In this video, we'll continue talking about the reactivity of aldehydes and ketones, and we'll look at two kinds of nucleophiles, nitrogen and sulfur containing nucleophiles. First thing we'll look at is primary amines, how they react with aldehydes and ketones to give a functional group called an imine. Then we'll look at secondary amines, which form enamines, and finally thiols form thioacetals. So what's an amine? Well, if you have an aldehyde, so let's see here. So if you have an aldehyde or a ketone, that will react with a primary amine, like methylamine, to form an imine. An imine is a carbon-nitrogen double bond, so the nitrogen has a lone pair of electrons. It's making three bonds, one of which is a double bond to carbon, and it brings whatever group that it was bonded to with it. One way you can think about the formation of imines is that the formation of an imine is always going to be accompanied by formation of a molecule of water. So if we look at the structure of our primary amine, we have methylamine here. So in the product, we lose these two hydrogens and this oxygen to form H2O, and this nitrogen becomes double bonded to the carbon and it carries with it the methyl group. So that's the imine formation. So when you're thinking about the mechanism for this reaction, if you want to know how it works, right, first thing you want to do is ask yourself, are the reaction conditions acidic or basic? These reactions are always carried out under using an acid catalyst. Okay, once we know that, then we can propose at least the first two steps, as we've talked about before, and then from there we should be able to come up with some sensible steps to take us from our starting materials to our product. So let's do that on the next slide. Okay, for the sake of time, I'm going to simplify the structure of my aldehyde a little bit. So let's say we had this aldehyde reacting with methylamine, and let's say we used toluene sulfonic acid as our catalyst, and our product is going to look like this. We have a CH3 and a lone pair of electrons on nitrogen and a hydrogen. This is our imine product. So let's propose a mechanism, right? So just like in the acetal formation video, right, the first thing that's going to happen when we mix together toluene sulfonic acid and our amine is that our amine is actually going to accept the proton. So just like in the acetal formation video, any proton transfer is going to come from protonated solvent, and any time that we need something to accept a proton, then the solvent is going to do that as well. So with that in mind, right, we're going to start with our aldehyde. We're under acidic conditions, so odds are that the first step is going to be a proton transfer step, and that's going to come from a molecule of solvent or our reactant that's protonated. So we need to protonate the oxygen to make it into a better electrophile. So we transfer a proton from protonated solvent to our aldehyde. Now that's protonated. And now this carbon is electrophilic, right? So now we get a nucleophilic attack step. Remember, the amine in this case is our nucleophile, because this video is about nitrogen-containing nucleophiles. The nitrogen attacks the carbon, which breaks the pi bond, giving us a tetrahedral intermediate. We'd have an OH and an N with two H's and a CH3 and a hydrogen, and this nitrogen has a positive charge, right? Okay. And then, just like in the previous video, we need a proton transfer step to make this molecule neutral. And again, our methylamine will be, and this should be a 2 here, will be our base. So we'll accept one of those protons. So this, so far, looks exactly like the formation of an acetal, right? And this would, at this point in our mechanism, we call this a hemiacetal. This with the nitrogen and oxygen is called a hemiaminal. And then we have the same series of steps that we had previously, right? So now we want to get rid of a molecule of water, and to do that we need to transfer a proton to our OH to make that into a good leaving group. So we're going to transfer that from our protonated amine. So that is a source of protons. We transfer that guy like this. So now this is going to be a water molecule. So we have a and now we have a leaving group leaving step, which generates that molecule of water. That's also one of the products. And a carbocation. So this is where things get different, right? Because what can happen now is that we can draw a resonance structure of this compound, right? Where this lone pair of electrons becomes a double bond. So instead of drawing an equilibrium arrow, we'll draw a resonance arrow. We have a double bond to nitrogen, CH3. Still has a hydrogen on it, so it's got a formal positive charge in the resonance structure, right? But now, unlike the acetal version, right, nitrogen can lose a proton to become neutrally charged. So the last step is a final proton transfer to amine, to enamine. So we transfer the proton, and what we get out is our imine product. So that becomes a lone pair of electrons, and we get our imine product. So the mechanism is very similar to acetal formation, right? We have a proton transfer to the oxygen, followed by a nucleophilic attack, followed by a proton transfer to give us a hemiaminal instead of a hemiacetal, right? We transfer a proton to oxygen to the OH to make that into a good leaving group. That leaving group leaves. And now the only difference is that we can draw a resonance structure that possesses a carbon-nitrogen double bond, and then proton transfer gives us our imine product. Okay, so that's what happens with primary amines. With a secondary amine, let's say instead we use dimethylamine. So now we have a secondary amine and an acid catalyst. Instead of getting an imine, we get an enamine. Ene because we have an alkene directly bonded to an amine. So this kind of a compound is called an enamine. Okay, so let's quickly go over the mechanism. It's actually very similar to the previous one. So let's just say we use the same aldehyde, and instead of methylamine, we'll use dimethylamine. Now our product is going to be this enamine. Okay, so most of the mechanistic steps are going to be very similar, so I'll go through those a little bit more quickly, right? We have our aldehyde. The first step is going to be proton transfer. We have nitrogen. We have a protonated version of our amine, so that's going to have a positive charge. We transfer a proton from the nitrogen to the oxygen, so we get our protonated aldehyde, which then undergoes nucleophilic attack by our secondary amine. We break our pi bond, we get this tetrahedral intermediate, right? And we have nitrogen and hydrogen and methyl and hydrogen, and then we do a proton transfer to dimethylamine, to neutralize that charge. So we get to our same hemiaminal intermediate, we have two methyls on there and a hydrogen. We need to transfer a proton to this OH, which is going to come again from our protonated amine. Okay, so we transfer a proton again from the nitrogen to the oxygen, make that into a good leaving group. And then that leaves, and we get a carbocation intermediate. Okay, I'm just going to erase this and redraw that intermediate so we can talk about it in a little bit more detail, because up to this point all the steps have been the same. We had proton transfer to oxygen, nucleophilic attack, proton transfer back to the solvent to get our hemiaminal, proton transfer to oxygen to turn that into a water molecule, water leaves. And that's going to give us a carbocation intermediate that looks like this. So we have the nitrogen and the methyl, and we have a positive charge here and a lone pair of electrons, right? So this is again looking pretty similar to the previous example. We have a resonance structure here where we can form our carbon-nitrogen double bond just like before. Okay, now we see what the problem is, hopefully. So when we were making an imine, right, we could get rid of a proton on nitrogen to neutralize that charge, right? But in this case, we don't have any hydrogen that we can remove from the nitrogen. So instead of removing a hydrogen that doesn't exist, right, what we can do is actually remove a hydrogen on the carbon next door. So let's say we have dimethylamine as our base. This, you want to think about this kind of like the same mechanism as an E2 reaction. The nitrogen is going to accept that proton. These two electrons are going to become the pi bond, and these two electrons are going to become a new lone pair of electrons. So this is still a proton transfer step, and thus our product is going to have a new pi bond between these two carbons. This is a single bond with a lone pair of electrons and a hydrogen, and that gives us our enamine. Okay, so just to refresh your memory, right, and depending on what we choose, if we have a ketone, for example, with a primary amine, all the steps leading up to this point are exactly the same. But for an imine, the last step is proton transfer to give us a lone pair of electrons on this nitrogen, and we deprotonate the nitrogen. For a secondary amine, the last step is deprotonation of the carbon because there's no proton on the nitrogen, which becomes a pi bond, carbon-carbon double bond, and this double bond becomes a lone pair of electrons on nitrogen. So that's the difference between imine formation and enamine formation. Okay, so what are imines useful for? Well, one thing that's really useful is the Wolff-Kishner reduction. So one thing that we can do is make a special imine called a hydrazone. So if you take a ketone and react it with hydrazine, this molecule NH2 is called hydrazine. Reaction of hydrazine with a ketone and an acid catalyst gives a hydrazone. And treatment of a hydrazone with a strong base like potassium hydroxide, water, and heat leads to reduction. So you get the net result going from here to here is called the Wolff-Kishner reduction because you're deoxygenating. You're going from a carbon-oxygen double bond to an alkane. You go from a ketone to an alkane, you lose that oxygen and replace it with two hydrogens through the intermediacy of a hydrazone. The mechanism to make the hydrazone is exactly the same as imine formation, so I'm not going to talk about that. But I will talk about what's the mechanism for going from your hydrazone to loss of the hydrazone to give cyclohexane in this case. So the first step, we have hydroxide. So now we're on strongly basic conditions. So the first step in this case is actually deprotonation. We lose a proton to get a negative charge on nitrogen. We have a negative charge here, which has a resonance structure, right, that places a negative charge on our carbon, and we have a nitrogen-nitrogen double bond. We have a lone pair of electrons on carbon. So the solvent is a water molecule. So the next step is proton transfer from the solvent. So this picks up a hydrogen, and we regenerate hydroxide. So that gives us one of our CH bonds, right? So we're going to end up with two CH bonds. One came from protonation of the negative charge on carbon. The next step is a second proton transfer to hydroxide, which is a strong base. It deprotonates the second NH bond. And just like before, what we can do is say this is going to have a resonance structure. And actually, what can happen is that now we don't have a resonance structure. What can happen is that we form nitrogen gas, and at the same time we break that single bond. So instead of a resonance arrow, we just have a product where we have a negative charge on carbon, and we form nitrogen gas, which is N2 here, and then that can pick up a second proton from a water molecule to give us back our hydroxide and cyclohexane. Okay, so to summarize everything, the mechanism for formation of acetals, amines, and enamines is all very similar, right? The first three steps are always proton transfer, nucleophilic attack, proton transfer, either to form a hemiaminal or a hemiacetal, hemiaminal or a hemiaminal, or what they call a carbonylamine. And then formation of an acetal is proton transfer, leaving group, nucleophilic attack, proton transfer. The difference in amine formation is that you just get a proton transfer without a second nucleophilic attack. Okay, so just like acetal formation, we can reverse. So remember, since water is a byproduct of these reactions, water is formed as a product of amine formation and water is formed as a product of enamine formation. If we take an amine or an enamine and react it with a large excess of water, that shifts the equilibrium back to the ketone. These are equilibria that can be shifted depending on if we have a lack of water, we're going to go in this direction. If we have an excess of water, we're going to go back to the ketone stage. The last thing we're going to talk about in this video is thioacetals. These are exactly the same. The mechanism to form these is exactly the same as that to form cyclic acetals, right? Instead of having two OH groups, you have two SH groups. And in the presence of an acid catalyst, you can form a cyclic thioacetal. These are useful because in the presence of Raney nickel, we can desulfurize. So Raney nickel has a bunch of hydrogen absorbed on the surface, so we can replace these carbon-sulfur bonds with carbon-hydrogen bonds if we had cyclohexane here. Again, this is a way to deoxygenate a molecule, so you're replacing a carbon-oxygen double bond with two carbon-hydrogen bonds. Okay, so I know there's a lot of information that's been thrown at you, so let's summarize, right? Primary amines can react with aldehydes and ketones in the presence of an acid catalyst to make amines. Amines are useful, and one example of the utility of amines is the Wolff-Kishner reduction. We can deoxygenate aldehydes and ketones. You can use secondary amines to make enamines. The mechanism is the same except for the last step. We can hydrolyze amines or enamines, which is basically the reverse of their formation, by just performing the reaction with a large excess of water. And I want you to be able to draw all forward and reverse steps for acetal formation, amine formation, and enamine formation. And lastly, we looked at sulfur-containing nucleophiles. Those form thioacetals, which can also be desulfurized in the presence of Raney nickel.